Gosh darn this. Okay. Okay, those of you watching the recording, I just walked through a whole explanation of this. So I'll walk through it again really quickly. I'm sorry for the folks who are here. Um, but okay, so again, right, number of islands. So in this one, we have a two-dimensional grid, m by n, where those numbers represent a dimension. Um, and the grid is composed of a series of ones and zeros. So you can sort of just visualize this by looking here, where one represents land and zero represents water. And the goal of your function, num islands, is going to be to return the number of islands in the grid. And so the general rule is that an island is defined as an island is entirely surrounded by water, and sort of formed by adjacent lands. And you're considered sort of adjacent if you are horizontally or vertically connected. So the thing we called out was it wasn't diagonal. And then we also have this assumption, you may assume all four edges of the grid are surrounded by water. So looking at this example here, so we can sort of see here, we have all of these ones here, and then this thing juts out here, but because it's connected here, this one here is more of a peninsula connected to this bigger island. Same thing over here, so we can sort of see here, this is just one big island, and then here's the water. And indeed, the output is one. And this next thing here, we see there's three islands, and that sort of corresponds to we have like an island in this top corner, an island here in the middle. Again, diagonally, but that doesn't count, right? There's no actual sort of diagonal connection there. And then we have an island in this bottom corner. So again, the challenge for us is if I feed you a grid, tell me how many islands are in it, given these rules. Okay. All right, back where we started. All right, so now, based on that, any thoughts on how we might go about doing this?
I guess I'll just unmute. Only one here.
Yeah.
Uh, I'm thinking check horizontally first for the ones and zeros. And then if I can't get once I hit if I'm at a one, obviously keep checking until I hit a zero. And then so I found the horizontal boundary and then do the same thing vertically. But at that point, traverse the boundaries to see where the island ends.
Perfect. Yeah. Perfect. Yeah. So your instincts are exactly right. So the first thing that you want to set up, and again, and I'm gonna talk about traversals and everything. We're gonna come back to that. But I think already the general framework is there, right? Which says I have this grid. I know I'm gonna loop through the grid. I'm gonna look zeros and ones. When I find a one, I know I found an island. I just need to figure out the extent of the island. And I think, and that's what's a little bit challenging about this is it's not, at first pass you might be like, oh, just count the number of ones, right? But that doesn't work because you need to sort of figure out whether or not that one is part of an island or not, and part of an island that you've already counted or not, right? So, as an example here, like this one is clearly it's an island onto itself, whereas this one here belongs to an island that theoretically you've already counted. And so, yes, so your basic intuition is exactly right to say, find a number one, find an island, and then traverse it, basically sort of exhaustively search for all the land that's attached to it. So yes, so that is exactly where we're going to end up. To do that though, I'm going to go back here. Let me see here. Okay, so where's my graphs? Okay, so yeah, so graph models are sort of a foundational kind of programmatic structure for modeling all sorts of things. And we use this, we can think of it as sort of physical processes. So doing things like networks, connectivity, things like physical things where there's sort of graph things. But I think where it's more commonly used and more utility oftentimes is in processes. So thinking through sort of process models. And in fact, the things, and so, again, apologies, I'm sort of giving the run through something like this is generally speaking, graphs are composed of nodes. So you have, an existing sort of node, and it can be a location, a process step, a gameplay state, something like that that's considered sort of a static node. And then you have these edges that sort of connect these processes. Basically, rules that says you can traverse from one thing to the next, but only these. And sometimes they're directed, sometimes they're not directed. Oftentimes they're weighted, which says we assign relative sort of cost to traversing from one particular node to another. Sometimes we do, sometimes we don't. But there's a lot of sort of ways in doing this. And this is sort of a really popular way of modeling out any number of processes. And in fact, the example that I give that I sort of love is gameplay, because it's actually kind of an interesting thing. Like if you take an intro to AI course, one of the fascinating things that they'll talk about is like, what is AI? Because we've now gone through multiple generations of AI, and each time has been different things. Like you talk to somebody today, they'll tell you it's LLMs, generative AI, right? That's AI. 5 years ago, AI was machine learning. Yeah. 10, and then, 20 years ago, it was graph traversals. And what I mean by that is, I don't know if you guys remember, but like during the 90s, the big thing back then was like supercomputers beating humans at games. Like it was Deep Blue, right? Do you remember? Yeah, like when he went up against like Gary Kasparov, and there was like a big deal, like the supercomputer beat Gary Kasparov. Um, Man, poor Gary. Like I love how this guy, like he was this, he is like this really actually accomplished guy, but like everyone only knows him because he lost to IBM Deep Blue. Like that was his thing. But so the question is like, how do systems like Deep Blue play chess, right? How do they do that? And the short answer is they use graphs. So the basic idea is, are we here? Well, do I have a marker before I do this whole thing? I do. Does it work? This is intriguing. I didn't even know I had a marker. Okay. Let's stop sharing so I can make myself. Eh, okay, I guess it'll work. Okay. So basically, I mean, and this is the way sort of most strategy games worked. You would have a sort of a game board, which would be sort of a state, and that would be a node. So this is like the current game board as is. And you would hard code the rules of the game. So, think about chess. Like there's a certain number of allowable moves you can make. And so each of those moves would then represent sort of, if I moved this pawn versus this pawn versus this pawn, these would be different moves you could make. And so, you'd have it sort of connected there. And then based on what that game board would be, there would be another series of moves that, again, would be hard coded. Right, and so on and so on. And so what these, at a very sort of high level, what these programs would do, is they would basically sort of expand out the game and essentially just sort of run the game out to its completion. I mean, if taken to an extreme, you could literally expand out the entire game and then just sort of count up wins and losses and just probabilistically say, oh, if I go down this branch, this gives me the highest win percentage. Right. This branch I win 60% of the time, this branch I win 20% of the time. I'm going to choose this move. And then the computer would just always pick the move that had yielded the highest probability of a win. And that was, and at very high level, very crude level, like that's what AI looked like. Like that's what they were doing. Now, and that's why, by the way, the reason why like certain games were harder versus simpler was this, what we call the branching factor. How many possible permutations of moves you would have to factor out, which is why I don't know if you know, but like what was considered like the hardest game for AI to crack?
Go?
It was Go. Yeah, it wasn't chess. It was Go because
I think that was in the movie Beautiful Mind.
oh, was it?
I think so.
Oh, interesting. but it's because of the branching factor, right? It's not all the moves, it's not everything. It's just you had so many, you know, pl positions you can place the little tiles on the board. So that's what sort of did it. Okay, I'm
So
gonna,
like,
yeah,
um, so the issue with Deep Blue and Kasparov was that Deep Blue already mapped every possible move. So whatever move Kasparov did, Deep Blue already knew ahead of time. Okay, so if my opponent does this, then my best move, it already had the possible permutations of which move to.
pretty much. It at some point though, it gets actually too computationally, um, I mean, so that was where the supercomputer thing is, right? At some point, it gets too computationally intensive to do it this exhaustively. So what ends up happening is you start doing heuristics. You won't go out all the way, but maybe you'll play out the next 10 moves. Or, and so you'll use different heuristics within that. So if the game is simple enough, yeah, you can just do it exhaustively. But even when you don't have the raw computation to do it exhaustively, you can still do it sort of comprehensively. Like, yeah. So exactly. That's why, I mean, that's why it's so hard to beat these things. They literally will play out every permutation and be like, yeah, I win 80% of the time if I do that branch. So, and it's an interesting aside because I oftentimes when I lecture about AI, I love giving that example because to me it's a perfect example of like intelligent outcomes from fundamentally unintelligent processes. Right? I mean, there's nothing intrinsically intelligent about this. This is just raw compute. You're throwing processing power at something. It's just probabilistic sort of processing. But we get these really impressive, again, right? Even just your chess game on your phone now will trivially beat even a grandmaster. Um, so yeah, so it's kind of, but again, sort of an interesting sort of analogy to the fact that like we assume that intelligent products are the result of intelligence and right, or at least cognition, right? Understanding. Like you have a conception of chess, you know the rules, you know the strategies, the moves, maybe even the history, right? Computers, no, it's just like I'm gonna build a tree and that's it. So but anyway, so I think, again, bringing it back to the island problem, and let me share the screen because I really don't want to stare at my face magnified at the thing. So yeah, so the notes we talk about this a little bit, about sort of just graphs and there's different ways, by the way, of doing it. And I'll sort of talk about, I'm running ahead with this, but generally speaking, there's sort of two ways, what we call breadth first and depth first. Um, Okay, actually, this is a good way of looking at it. Breadth first basically says just sort of exhaustive traversals. Like if you're doing this, actually, you can sort of see the numbers here. If you start at node one, you expand out all possible nodes. We call this, it's a queue versus a stack. So a queue says you expand out, you check this first, you go to the next row, you check these, you expand out, you load the next thing, you expand that out, you go there and that. And it's sort of you search each layer by doing it. Depth first is a stack. You're basically sort of constantly throwing things on the pile. So you start here, and then you just go a certain way. And you say, okay, I'm going to go here. And then if that doesn't work, you throw another thing. And you check that. You throw another thing on.
They need to see that. They need to turn it.
Oh, am I?
You're
Oh,
not pointing, so.
oh, okay. Okay. Well, sorry. For the guys who are watching home, these numbers represent the order in which the graph is traversed. So like, again, sorry, if you look here, again, you sort of breadth first is sort of exhausted by each row, right? So you start at this thing, you expand out all possible nodes, you load them into the queue. So think about like a line where first come, first serve. So you do this, then you expand out, then you search those. If those don't work, you expand out the next line, load it into the queue, look at those, expand out, look at those until you find your result. Depth first search is what we call a stack. You basically just kind of keep throwing options to the top of the list for review, and then you just kind of review them. So again, you start here, I choose just a node and I traverse it. And I say, okay, didn't find it, just choose another one, traverse it. Choose another one, traverse it. Okay, I ran, right? I came to the end of this particular branch, backtrack, what's my next available one here? Do that one. Okay, I'm done, go back here, go back here, go back here. Again, this is what we call a stack. Last in, first out. So
Got it. Thanks for reviewing that.
what was that? Sorry, what was that, Era?
I said I got it. Thanks for
Oh,
reviewing that with the visual.
my pleasure. Yeah, visuals definitely help. The thing with both of these though is that um, they both are designed to be exhaustive. And I know that depth first sort of feels more arbitrary, but this is designed to be exhaustive, although depth first does have challenges because, and we get into the weeds with this thing. There's two problems with a depth. Well, there's problems with both. The problem with the depth first thing is it works when both of these are sort of limited graphs. Like here, we have a total of 12 nodes. Both of them will be exhaustive. Breadth first, depth first. We'll keep going um, until it thinks. If it's an infinite thing, the problem with depth first is you might go way down. You might go down a particular branch, like, I might go, 100 levels deep, whereas the solution was right here and I missed it. So that's a problem with depth first. Another problem with it is also oftentimes you're asked to find like shortest path. And that's a very common CS problem is shortest path, nearest solution, things like that. And so depth first will not necessarily get you shortest path because again, it doesn't do it layer by layer. It just kind of it opportunistically goes down a particular branch as far as it can go. And again, right, it's not necessarily there. Now, having said that, it also, because it's less kind of, breadth first is more plotting, it does give you a little bit of a random factor that says you can find things sooner. So, but yeah, either way, you are generally speaking, it's going to be comprehensive. Um, it's just again different ways of how you load these nodes as you encounter them. Do you do it a queue where first in, first out, or do you do it as a stack where again last in, first out? Okay. So and yeah, then there's more stuff here. And we'll sort of talk about stuff like that. But I think in order to do this, the important thing for us to know for our LeetCode problem is that we're going to do a breadth first search implementation is what I'm just kind of going to get there. So going back to LeetCode and so Kern, you sort of already kind of had the outline for this. Basic idea, right? We're going to loop the grid. When we encounter a one, we know we've hit an island. And our question now is, okay, what is our island? How big, how encompassing is our island? And so the idea here is we're essentially going to implement a breadth first search. We are going to, within this island, we're going to sort of load this island, this particular grid into the queue. We're going to expand out. We're going to navigate both vertically and horizontally, expand out, and we're going to see whether or not those are also land. If they are, we're going to load them into the queue, expand out, expand out, expand out until we've sort of encountered all of the land. And then we go sort of, and again, we sort of iteratively go through traversing it. One critical thing that we're going to do though, well, this is one sort of critical step that I didn't really appreciate when I first tried to tackle this, is we're going to what's called flood the island. Not flood, we're literally in this case going to flood the island, which says that when we encounter land as part of this sort of queue, once we visit a node, we're going to flood it so that we don't then, if we sort of encounter it again, we're not going to double count it. Basically, we're going to say, okay, we already counted it. It's already part of our island. We're not going to sort of do anything else. So I'm going to basically flood it as I visit it. So I'm going to say, okay, this is island. Okay, this is island. Flood it, flood it, flood it, flood it, right? And that way, and so, for instance, so we're going to sort of build up a queue that's going to sort of encompass these. We're going to flood these. We're going to keep looking. We're going to counter this. Nothing else. We're then going to keep going, counter this, load our queue, and flood that. So that's generally the approach that we're going to take for doing this. Any questions on that? Okay. Now, I will say, we are going to use sort of a specific sort of queue library for this. That makes it, I mean, there's a way to sort of do this manually, but I'm going to, there's a particular queue library that we can sort of use that will make it a little easier. So I'm going to just kind of do this with you guys, if that's okay. So yeah, okay. So let's just start coding this up. So again, so remember, this is sort of a two-dimensional thing. So we're going to need sort of horizontal and vertical. So I'm going to get those two dimensions. So I'm going to say M and N. And these are going to be equal to, so to get the dimension of, so if you think about this as like a stack of these sort of things sort of stacked together, which is a two-dimensional kind of list. So this is going to be the length of the overall grid. It's going to be one dimension, length of grid. And because if you sort of see here, right, so grid is basically a list of lists, is basically a way of thinking about it. So, this one sort of dimension here that would be vertical was just the length of this. So in this case, there's 4 rows here. So that's going to be the length of that. And then if I want to find out the length of, in this case, the rows, I just take the length of the first list, right? So M is then going to be length of grid 0. And again, I can take any of those rows, but again, the idea being this gives me height, right? Because it'll tell me the number of rows. This tells me the length of each row. So now I have sort of the length of my two-dimensional grid. Now I'm going to sort of need that for my loop. Okay, so that's the first thing we do. And then the second thing we're going to do is we're going to make a counter. So call it islands, and we're going to initialize it to being 0. Ultimately, spoiler alert, right, we're going to return the number of islands. So as we go through, we encounter islands, we're going to sort of return that. So that's where we're sort of building towards. Good so far? All right, so let's do this loop here. So now I'm going to say I'm going to call R in range. And so the first thing I'm going to do is, so this is going to be a nested loop. So I'm going to loop M first. So for R in range M, and then I'm going to say I'm not sure why I chose these numbers, but whatever, for C in range N. So again, so nested loop for that. So the first thing is, okay, so now if I find, land, so, land ho, right? So that would be if that particular location in the grid, so that particular location is going to be grid R, C is equivalent to 1, right? So essentially we're going to do sort of an inner and outer loop.
Strings.
Oh, thank you. Yes, you're right. That would have thrown things off. Good catch. Right, so as I'm going through, again, so if that's a 1, if that's a 1, if that's a 1, right? So if these are 1, so the first thing I'm going to do is I'm going to increment islands plus equals 1. Okay, I have found a brand new island. This is great. Now, I'm going to create a brand new queue. Right, so now I've found this island here. I'm going to then so create a brand new queue. I'm then going to add that particular thing to it. And I'm going to then flood that tile. Okay, so that's going to be sort of the first step. So I'm going to visit this node. I'm going to add it to my queue, and then I'm going to flood it. So that's going to be the first thing we do. So I'm just going to sort of even just indicate this. So BFS steps. All right, so first thing I'm going to do here is I'm going to say brand new queue equals, and again, this is where you're going to use the DQ library. So, and this is something we haven't learned and we haven't done before, so that's why I'm going to sort of introduce you. So this is basically just kind of you're essentially creating a queue on the fly for this. So now that I've created that, so I've created that queue object, and I'm going to, and it works just like a list. I'm now going to append a tuple with those 2 elements there. So those are going to be added to the queue. And now, because I'm visiting the queue, I'm going to now mark it as visited. And in that case, what marking as visited means is I'm going to flood it. So now grid R C is now equal to 0.
Get to zero.
Oh, yeah, no, it's
Confused with water.
well, that's the point. That's exactly the point. I'm basically I'm flooding it by saying because if I encounter this again, I don't want them to accidentally double count the island. So I mean, yeah, you're right. I could change it to any other number, but the idea here is I'm literally flooding it. I'm saying I've encountered this. I've already sort of reached this part of land. If I'm, I don't want to encounter it again, basically. So yeah, so I'm literally in this case flooding the land. Okay. So and again in graphs that's the same notion as sort of marking it as visited. Because you could do that too, because that's a more sort of typical thing is exactly that. You keep sort of a list of nodes that you've visited, and then when you encounter a node, you often do a lookup, be like, hey, have we been here before? Very common, particularly like with depth first search. When you're like backtracking, you're like, oh, have I visited this node? Oh, no. Okay, add to the stack, or oh, I have, right? So yeah, so marking as visiting is sort of a critical thing. So that's kind of how we're doing it in this case. Okay, so now we need to sort of pop out the next list here, right? So if you look at this kind of, where is my deck thing here? Right. So again, when we visit a node, part of what we then do is we say we pop out or we expand the node. So and we see all the edges that's available to it. And if we encounter those edges, we then add them to our queue, basically. So that's what we're going to do next as our step. We're going to sort of pop this node and add these to the queue. All right. So, and for this, you can just say while queue, because simply while basically while the queue is populated. So the question I'm going to say, I'm going to say X and Y equal, and I'm just going to be perfectly transparent on this. I had to look this up. It's not like I knew how to do the code for BFS thing. This is something I had to look up. Q pop left, right? So this is sort of equivalent of saying like, I'm going to extend it and I'm going to try to see what's traversable with it. So now I'm going to say, okay, now I need to figure out whether or not any of these are valid as, as options for myself. So I'm going to pop left. I'm going to say, okay, for each of these, I'm going to say for dx and dy. So I'm sort of creating sort of placeholder, sort of two positional things in, and I'm going to sort of do an array of options for me based on relative position. So either moving to the left, okay, to left, moving to the right, or is that the opposite? That's the opposite. Yeah, moving to the right, moving to the left, moving down, and moving up. So this is the four, right? Because it's either vertical or horizontal. So, and again, because, right, arguably, theoretically, we don't necessarily need to look up or to the left, because theoretically, if we're looping this way, in this way, like we shouldn't encounter this. But the whole idea is that we're just being comprehensive. Every time we encounter a one, we're immediately going to look at all of its immediate neighbors. And again, part of the advantage of flooding it says, like in this case, these will have already been flooded, right? Because we've already flooded that. So when we hit this one, we try to expand this, we've either encountered it or it's just not valid. And so that's sort of the advantage of doing that. All right, so those are the directions we're going to go. So now I'm going to say here, so I'm going to say nx and ny are equal to x plus dx. So again, so we're going to take the current x thing and we're going to potentially expand it out in the direction of dx, either again, positive or negative. And then y, same idea, y is equal to y plus dy. So we're going to sort of extend those out. And now we're going to test to check whether or not these sort of resulting coordinates are potentially valid to pop into our queue.
Then what does pop left return exactly?
I think my understanding is that pop left basically sort of opens it out and says, okay, we're potentially adding a new entry to this, basically, is sort of what
Okay.
yeah. But I may need to double check on that because I actually am not sure specifically what the pop left does. I think it's again the expansion thing, but I'm not sure because we are sort of hard coding the rules for the edges right now. So, um, so all right. So now to decide whether or not something gets into the queue, there's two things I want to check. The first thing I want to check is I need to make sure I'm not out of bounds, right? So for instance, if I'm right here, I'm going to get sort of index out of bounds errors if I try to go there. So the first thing I want to check is that I'm in bounds. And then the second thing I'm going to check is if it's a 1. If both of those are true, I'm going to add that to the queue. And then the idea is I add that to the queue, and then the queue then checks all the other nodes and then goes to the next thing, right? And then loads and loads and loads and loads until we've exhausted it. So, okay, so we're going to calculate this and we're going to say so basically we're going to say, because we're going to say nx, right? So nx, if nx is nested between 0 is not equal to nx and, space this out, m, right? So we want to make sure it doesn't go out of bounds there. And same logic here to ny, which is less than or equal to n. Okay, so both those have to be true. They can't be out of bounds. And we're so high maintenance here. Grid nx and y is equal to 1. This be a string. So if all of those are the case, then we append that. We do what we did here. We append it and we flood it, basically. So we're going to say q append, and again, we're going to append this as a thing, nx and y, and we're going to say grid nx and y equals 0. Okay. And so that's going to create our queue for us. So again, so the idea is when you encounter, so you're going to loop. So basically the whole idea is you're going to sort of loop through this. When you encounter land, you're going to add it to your queue, and then you're going to flood it. You're going to turn this into a 0. And then you're going to sort of expand out and you're going to say, okay, well, are there any other lands here? If they are, and in this case, these 3 are, load those into the queue, then traverse to each of those. And for each of those, flood it, expand out, see if those are in the queue, flood that, expand out, flood that, and eventually you'll have completely flooded the island. And then once you've done that, then your queue is empty. So your queue will no longer, you're going to exit the queue, and then you're going to keep traversing it. And the key thing is if you start here, by the time the queue is done, everything else will be zeros. So you continue 0, 0, 0, 0, 0, 0. In this case, it'll just return 1. So that's what that is designed to do. Okay, now, ultimate thing for us, we're hopefully basically there. I need to return island. Okay, my indented, so that's class, that's def, so we should be here. Yep, okay. All right, let's run this and see if this works. Oh, did I time out? Oh, hang on. Log in. That's frustrating. Let's try that again. Okay, let me just try to run it without. Here, can I submit? Okay. Well, that's frustrating. I don't think so. Stuck here. Yes, I am stuck here. Widget keeps looping. Okay, I am human. I consent. Great. Let me in. Verify I'm human. Yes. Well, that was anticlimactic. Okay. Are you able to run it?
I type what you type.
Oh, okay, fair enough. Okay, I'm gonna pause the video. Oh no, that doesn't. That pauses the screen share. I'm gonna pause. Have a good evening. Okay, I am back. All right, so I'm going to test this. I haven't actually tested this, but let me run on my test cases. Runtime error. Okay, where's my next index out of range? Ooh. Okay. Ooh, let me see here. Where did I go wrong here?
No, mine works. One thing, the grid NX and Y.
Oh, it can't be less than. It has to be less than, not less than equal to.
And
Be-
also, oh, okay.
So that's one mistake because the whole length thing, it's going to be -1. So that has to be, it's less than or equal to 0, but it's less than the upper bound. Okay, so let me see if that did it.
But also at the very end, grid and the flooding, you put,
Oh,
yeah,
what did I do?
you did 0 instead of string 0.
Oh, thank you. Yes. Good catch. Yep. All right. Let me run those.
Case C failed.
Okay. Let me check my code here. So I'm gonna submit and okay. This passed all my things. Okay.
It's like,
Should I take a look?
let me check your code again. I might have done a tab of what's it called? Q or yeah. Jeez. Okay, yeah, I did this. I didn't have the while loop inside the floor.
Okay. Yeah. Oh, yeah. Yeah. It's nested within the for. Yeah. So, yeah. I mean, again, sorry, I'm monologuing a little bit, but I think right. This kind of illustrates for these things in terms of just raw sort of talent from a pure Python perspective. Again, there was a particular library we used that we hadn't used before. And I did, slightly more complex syntax in terms of sort of nesting variable assignments and things like that. But for the most part, like this is all stuff that we've done and are familiar with. Again, at this point, this is just kind of knowing the recipe, knowing that you can do something like this, that you can approach this as a graph traversal and just seeing them be like, oh, this is a graph problem, right? So, and yeah, like I said, many problems are formatted this way. We talked about gameplay. As you can sort of see here, this, it's just kind of begin to see the pattern and say like, oh, right, this is, okay, I find land. I need to discover the extent of the land, right? I need to discover exactly how far this goes because I can't just do a raw count of land. I have to decide what's part of a particular landmass or not. And so seeing that, I should be like, oh, graph traversal, right? Um, and then be like, okay, I know how to do that. Again, it's the kind of thing, as we sort of keep practicing, we'll do. So I'll probably do at least one more graph traversal because again, those things are like so critical to so many core functionalities. So maybe I'll do one with a depth first search, which is a stack instead of a queue. And then we might do like shortest path type stuff. So that's what Dijkstra's is. So shortest path is looking at what happens if it's not just sort of finding, source to destination, but if there's different costs associated with different routes and how to do it. And so like Dijkstra's very famously is the algorithm for determining shortest path in a weighted graph like that. So I think those might be some good examples we'll work on.
We're actually doing queues in the data types.
You're doing which one?
In algorithms, data structures.
Oh, okay. Which one are you doing?
Oh,
Oh, queues. Okay, good. Perfect. Okay, yeah. So perfect. So, yeah, so queues, prep for search. All right, I will end there. Era, any questions on that?
Not at all. I'm just happy to be able to kind of watch you guys do that because I do see where these are things that we visited,
Mm.
but still wrapping my brain around it. So I'm going to be reviewing that. It's super cool though.
Amazing. Well, all right. I'm going to end the recording on that note.